Okay, here we go. Kinesiology 230, chapter number 3. We're in presentation number 8. Let's get rolling on this. We're going to talk about Krebs cycle a little bit further, fat oxidation, and then protein oxidation. This was in the last presentation. In the oxidative system, we talked about ways to remember the difference between NADH and FADH, and I brought up that I pretty much just had to remember it when I was an undergrad, and the only real mnemonic I came up with was F before N, and you get 2 ATP versus 3 ATP. So you get 2 for the F and you get 3 for the N. That's about the best way I can come up with, or I came up with when I was a student. I'm not going to belabor you with the process of the electron transport chain, but what I'm most concerned with is that you understand it's there. You understand it's part of a process to help create ATP. And this process of creating ATP is done through a process that cytochromes are carriers, and they carry the hydrogen atoms through the chain itself to help us create ATP. Way more complex than that, but for the sake of our class, that's as far as we need to go. So with the NADH and the FADH, just to reiterate, you get roughly 2.5 ATP molecules. It's mostly glycolytic, so you have glycolysis, pyruvate oxidation, and Krebs cycle. The FADH, you have flavin, adenine, dinucleotide, 1.5 ATP, give or take. Remember, it's more like a 3-2, right? 3 comes after 2 in the alphabet, and N comes before F in the alphabet. And the FADH is more Krebs cycle related. Now, these are listed in the chapter all over the place. And the big thing you need to understand is that each of these transport electrons between molecules. Both are similar to one another in terms of their function, but they differ in their ability to create ATP, and they differ in the amount that they can create, but they also differ in where they create ATP in the process. So let's jump into the oxidative system. We'll talk about fat oxidation, which I mentioned that just a little bit earlier in the earlier presentation, where we talk about beta oxidation. But fat oxidation, you take these triglycerides that are stored as fat cells, and they can be broken down by hormone-sensitive lipase. It's an enzyme, and again, lipase, ASE, lipo or lipid is a fat ASE enzyme. I hope you're starting to put this together. Lipase releases free fatty acids into the blood to circulate and enter muscle fibers. The fatty acids themselves enter the mitochondria where they can go undergo beta oxidation. So you have these triglycerides, and you have this hormone-sensitive lipase that gets involved in the process, and it breaks down the triglyceride into free fatty acids. These free fatty acids then circulate in the bloodstream, denoted here by this kind of cylinder that denotes a vascular system, and then it enters the muscle fiber itself. And you remember this from earlier in our class in terms of the mitochondria. And the free fatty acids that you have, they end up entering the bloodstream and the muscle fiber, and then you go into the mitochondria. That's kind of that purple thing here if you want to blow your screen up. That was the purple, and that's where it undergoes beta oxidation. So really what happens is you're taking these triglycerides and you're already breaking them up into free fatty acids, and the free fatty acids then go into the muscle fiber itself, where the mitochondria takes them through a process of beta oxidation. So now this is a series of reactions that causes the free fatty acids to be broken down yet even further, and this yields acetyl coenzyme A. And as we talked about previously, acetyl CoA is what goes into the Krebs cycle for fat oxidation or for beta oxidation. Now, protein oxidation, it's not a significant source of energy. The book lists that also protein is broken down into amino acids, which is factually correct, but they list it's not a significant source of energy. And amino acids are converted into glucose, pyruvate, and others to produce ATP. And they're mostly branched chain amino acids, and BCAAs had their place. I mean, I remember years ago, that was a thing. Like you would actually drink like a little cap full of BCAAs post workout or before workout, just to make sure you had some BCAAs in your system. What I just want to point out here is when you look at this is an area that bothers me with this book, and I just want to point this out. When we look at these two side by side, one of them is one that you're familiar with. This was a pop out from the entire cycle, talking about the Krebs cycle. We talked about this before, and then they try to give another version of it in the book. What I don't like about it is the lack of consistency. And what they have in this rendering is they're talking about, for example, fatty acids. So earlier, fatty acids, beta oxidation. Got it. But when they actually show this again, they show the fatty acids are not in blue. They show it in kind of this gold color. And then you have protein, which is in a dark blue down here, but up here, the protein itself comes from the amino acids come from the protein being broken down. So what I don't like about this, and which can be confusing to a student, is here you are, you're trying to learn and dial in and carry a theme throughout a chapter. And frankly, I just think the authors dropped the ball here. I think they could have color codified this a little bit better to keep it consistent. So, if it's something where you have that kind of like visual learning skill where you're able to, like I color codify things, as I'm sure you've picked up, I would have color codified this better and kept this coloring consistent from one slide, one image to the next image to the next image, just so you know. But when you look at this, again, you look at where amino acids come in and the color of that should have came from protein. And then you have triglycerides, which would have came from fatty acids, just a sidebar. So when we look at the total energy yield from the oxidation of one glucose molecule, and this is something that you're going to find on a test question somewhere else. The actual process of glycolysis consumes 2 ATP, and that's if starting with glucose. So you know that's going to be somewhere on a quiz, right? Because that's such a specific setup for a quiz question. So glycolysis consumes 2 ATP. So the process itself, if we go ahead and go through and we create 40 ATP, you have to back out 2 of them. If you started with glucose, that gives us a net of 38. Just kind of remember that math for somewhere else. But if we look at this in terms of oxidation of an 18-carbon triglyceride molecule, which is a fat molecule, look at what you get. You get a mountain of ATP. So what you have is with beta oxidation and using fat for energy, it is a robust sort of energy, source of energy. And it's something where, you try to find, or you have the argument where people try to say, you try to stay in the oxidative side of the system. And I will tell you that, yes, that is true. And I will also tell you that if you're playing any kind of sport or doing any kind of activity where you're competing against other people, the luxury of being in the oxidative system and creating a mountain of ATP just ain't there, right? So it's just a matter of you're trying to find a way to ride that threshold between aerobic and anaerobic, and I say it all the time. So the big thing is, I don't want you to overthink this, right? When we start talking about this, and we talked about another slide where I'm like, don't overthink it. Just remember, you have ATP, as adenosine triphosphate, is needed for muscular contraction. If ATP is present, the enzyme, the ACE, right, does not go to the factory. There is no call. We do not need to create ATP. If there's ADP, adenosine diphosphate, in the muscle, then you have this isocitrate dehydrogenase. It's the enzyme that is stimulated, and the Krebs cycle factory, that's the Krebs cycle, the factory upregulates production. So just think this through, like I mentioned before. If you're sitting quietly and all of a sudden you decide to stand up, well, at that point you probably have plenty of ATP in the muscle, and plenty of ATP in the system. There is no call to the factory. We don't need to create any more ATP. But as you get up and as you move around, then you start to have the different catabolic reactions where we break up ATP into ADP, and all of a sudden there's ADP present. So with adenosine diphosphate present, then you have this upregulation of the enzyme. The enzyme then causes the Krebs cycle to upregulate production of ATP. So I can't stress this enough. When you think through this process, don't wig out about the NADH, the FADH. Just remember one of them is 2, one of them is 3. And just also remember, in terms of very simplistic terms, if there's ATP in the muscle, there is no need to call the factory to make more ATP. If there's ADP, then you got to make more. You got to make more phosphate. You got to have more of that to create ADP to have an anabolic reaction, because you've had a ton of catabolic reactions to break a phosphate off and create or to release energy out of the high energy bond. Again, keep it simple. Just think it through in terms of simple processing. All right, moving on to the next one.